So let's carry on in our discussions of work and energy. So as we mentioned last time, work is defined as the product of a force exerted on an object and the distance the object moves if it's in the same direction as the force. And so our equation for this is force times a distance. And again, we talked about this last time, and sort of our payoff down here is that so the units of work is newtons times meter, which we call a joule. And so that's our SI unit of work. And so now we're going to just expand this conversation, look at some different kinds of units, look at this idea of power, and also conservation of energy. So I sort of mentioned this briefly last time, but conservation of energy is this idea that energy cannot be created or destroyed, but can only be transferred. And of course, to transfer energy, you do that by doing work. And so that's how these two things are related. Work is how we transfer energy between places. So this idea is one of the richest and most productive ideas in all of physics. But like we mentioned last time, it's also much more subtle than other conservation laws, this sort of principle. And just this quote we mentioned last time, again, from a famous physicist, Richard Feynman, it's important to realize that in physics today we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It doesn't work that way. However, we have formulas for calculating some numerical quantities, and when we add them all up together, it doesn't change except for the energy coming in and out. And again, this is this idea, conservation of energy. And so here's a picture from the book, one of these tables, and it just kind of looks at the different forms of energy that we'll be dealing with in this class. And so we talked last time about gravitational potential and kinetic, the first two. We'll see that light, which comes in photons, is another way that we can, energy can, another sort of form of energy. Chemical energy and thermal energy, we'll talk a little bit about that today. Electric potential, and then eventually we'll get into this idea that mass and energy are actually equivalent. And here's just a little diagram to kind of show, how conservation of energy might work in maybe kind of a simple situation. So here's a situation of an apple falling from a tree. And so we'll start at sort of time 0. This apple is up here in the tree. And at that point, it's got only potential energy, right? It's not moving, so it has no kinetic energy. But because of the fact that it's situated up in that tree, it's got potential energy, because if it does, lose contact with the tree, it's going to convert that potential into kinetic as it falls down. And so if we imagine that that happens, then basically that process, you can imagine what happens is, so if it starts with 7 joules of energy, right, what happens is it falls down. If you were to take a picture and sort of look at it at this moment here, right, so what's happening is 2 of those joules of energy have been converted from potential into kinetic. The sum, right, 5 plus 2 is still 7, but it's changing forms. If you look down here at some later time, now it's even more converted into kinetic. So you got 3 joules of potential, 4 joules of kinetic, and then down here, just as it's about to hit the ground, it's got 1 joule of potential energy and 6 joules of kinetic. Again, the sort of idea here is that altogether, it's got 7 joules. And again, this is a really weird concept. When we talk about this in more advanced physics courses, at least I feel like this is one of the trickiest concepts we deal with. So we definitely want to spend some time trying to understand this. And one way that can be helpful is just kind of making an analogy to money. And so this little box here from the book. So a decent way to conceptualize energy conservation is to think of it as the money of physics. So it might change hands, but it's not created or destroyed. A large balance in a bank account is like a potential energy available to spend. So spending here would be like work, right? Basically transferring it from different places, and converting to another form like heat or kinetic energy. Is like the act of spending money. The rate of spending energy is called power, which we'll get to next. All right, so power is so a simple idea. It's just a way to look at energy per time. And so it's how much energy you're using per time. The more power you need, the more energy you need to use in a certain amount of time. So the general formula we use, again, with our SI units, the general unit for power will be watts, and watts are joules per second. So again, joules is our SI unit of energy, and so it's how much energy you're using per second. Another form of power that we use in our everyday life is horsepower, and that's equivalent to 745 joules per second. And so just the sort of the general idea is, if you do 100 joules of work in 1 second, then what we do is go to our formula over here. We do 100 joules divided by 1 second, and we get 100 watts, joules per second. And here we got a table from the book just kind of showing basically the power of certain things in our life. So like for a phone, we might have the units of, some number of watts. We'll look at some examples in a second, but 10, 20. For a microwave oven, you're talking then about kilowatts, so like hundreds of watts. For our campus, right, something large like our campus or our community, we're talking about 10 to the 6th, a million watts or megawatts, right? If you remember, mega is 10 to the 6th. Power plant or a city, gigawatts. If you're a fan of Back to the Future, 1.21 gigawatts, that's what that is. And then the societal scale, so roughly the amount of energy that our whole planet uses as a society is 10 to the 12th watts. And just here are the pictures. A Falcon 9 rocket puts out about 26 gigawatts of power. So quite, that's again pretty powerful example. All right, so let's look at some examples here. And so this first one, how much power does it take to lift 10 kilograms up 2 meters in 2 seconds? And so again, when you're looking at power, what you want to do is you want to look at the energy involved and divide by the time. So what's the energy here? Well, this is going to be gravitational potential energy. Okay, so that's m times g times h. And so the mass here is 10 kilograms. Actually, maybe I'll back up a second. Just do this a few more steps, just so it's super clear what I'm actually doing. So I'll do mgh divided by our time. And so what's my m? Well, it's 10 kilograms. Our g, again, we're going to approximate our g in this class is 10 meters per second most of the time. It's 9.8, but that's pretty close. And then 2 meters. So that's the amount of energy that you'll expel to lift up that object. And so if you do it in 2 seconds, then you get this here. When I went through and multiplied all this out, I got 100 watts as the power that it takes to do this operation. So again, the idea is energy per time. You got to figure out what kind of energy we're talking about, and then figure out what the actual time frame is. Getting to know the watt. So how much energy does a 100 watt light bulb use? So how much energy does a 100 watt light bulb use? And again, we got to get into these terms. What does 100 watts mean? Well, it's a rate of energy expenditure, right? And so it's basically, we're saying that that's energy per time. So it'll depend on the time that the light bulb is on. All right, so this is all about conversions of units then, to try to sort of figure out this and get to the bottom of this. And so let's look at this. So if I have 100 watts, so it's 100 joules per second, so I can use some units. And so for instance, I can multiply it by the special number 1 of 60 seconds over 1 minute. And so this will give us 6,000 joules per minute. So that's how much energy that the light bulb is using per minute. Again, 100 is how much energy it's using per second. And then I can go even further. So 6,000 joules per minute. And then multiply that times, again, our special number 1 of minutes per hour. And so we'd have 60 minutes per 1 hour. And when I calculate this, I get a huge number, 360,000. And of course this would be, again, canceling out the minutes and the minutes, joules per hour. So I think this is one of the trickier kind of units to get your head around, and we'll show some more examples here as we go through. But that's how you might want to think about it. So a light bulb gives off quite a amount of joules in an hour. And then again, one way you can think about power as something measured by a speedometer. So it's sort of how much energy you're using per time, rate of usage, where energy is more like your odometer. It's sort of how much energy have you used all together, the amount used. And so here's just kind of an example just to kind of get used to some things you might use every day. So here's a little power converter that might be 3 watts, something like that. Your laptop over there, 20 watts. Here's a 40-watt light bulb. That again gives off the brightness of a 100-watt regulation light bulb. So a television, the Sony TV, 265 watts. Microwave, again, it depends on which one you have, but we're talking more like 1,000 watts. So these are the things that kind of use more. A fan, a little heating unit here, 1,500 watts. A hair dryer, 1,800 watts. And then a washing machine that if you put it on its sort of highest setting using hot water and such, can get up to be like 5,000 watts. And so you can see that when you need to heat things, right, which kind of involves more energy, you're going to end up with more power. Just some kind of ideas of some everyday stuff. Here's some things from the book kind of doing the same thing. That's kind of giving you kind of an idea of what sort of just what some animals and everyday kind of objects, what sort of power expenditure we're talking about. So like a rat, when it's getting off like 1.4 watts. The laptop computer we looked at about 25 watts. So a large active human, 145 watts. Here's a cow, electric kettle. And to just kind of give us sort of an idea. Again, here's like a clothes dryer or a washing machine. And then here, again, that picture kind of showing just some more examples of that. All right, and so the last thing we'll talk about, again, is I think pretty confusing, so we'll spend some time on this, is the kilowatt hour. And this is the unit that our society uses a lot for energy. And so we'll sort of look at it here. So first of all, it's sort of weird, but if you think about it, so kilowatt, so kilo just means times 10 to the negative 3, right? That's what the K means. And then watt is energy per time. And so if you look at the kilowatt hour, right, you're going to have your units of energy per time. That's the watt. The kilo just gives us sort of a larger number. And then hour is time. And so the time cancels, and so this unit is just energy. But unfortunately, when we use watts, watts is typically done per seconds, and so times hours, it's kind of a weird way to do it, but it ends up being a unit of energy. And so this is what our power company charges us for. They compute how many kilowatt hours we use of energy. And so let's just sort of look at an example of this. So a television that I looked up online consumes power at a rate of 265 watts. The manufacturer estimates that a consumer will use 196 kilowatt hours of energy in 1 year. And so I was like, well, what does that mean as far as, how many hours a day are they assuming that we watch our television? And so let's look at this here. And so the first thing I'll do is say, okay, so we got 265 watts. Now what I want to do is I want to put that into units of kilowatts. And so I can do that several different ways. And so let's convert that into kilowatts first thing. And so what I do is I say, well, there's 1 kilowatt in 1,000 watts. So that's, again, 10 to the 3 is the same thing as 1,000. And so when I do this, what I'm doing this for is I want these watts here to cancel and be left over in actual watts. And so when I do this calculation, I get 0.265 kilowatts. And so this television, the power that it consumes is 265 watts, which is 0.265 kilowatts. And so they're saying that we use 196 kilowatt hours in a year. So they estimate that. And so what I'm going to do then is say, well, so I take that number of watts, 0.265 kilowatts, and I multiply it times time, which will be the number of hours. And then what this group here is saying, that it's approximately 196 kilowatt hours, like that. Okay, so this is a nice equation, and what I can do now is just divide both sides by 0.265 kilowatts, and over here 0.265 kilowatts. And so this cancels with that guy, and so I have left over just time. And over here, the kilowatts will cancel, and then it's 196 divided by 0.265. When I put this into my calculator, I got about 750, and if you look here, the last unit there is an hour. And so the time that they use to calculate this is 740 hours. And so then what I did is I said, well, that's over 1 year, and so I just took the 740 hours and divided by 365 years. And this works out to be almost exactly 2. So again, so this company here was thinking that we were basically oh, it looks like I made a mistake with my units here. Let me just fix that. And so the 365 is, of course, the number of days in a year. So the correct unit there would be day. And so it's 2 hours a day. And so they're estimating that's how much we watch television. Okay. And so finally, this can also kind of just make a little bit more sense with your power bill. So here's an example power bill I pulled off of online. And so you can look here that, you know, when they look at you and give you your bill, here's what they're writing. They're writing how much kilowatt hours you use. So in this case, this example is 426 kilowatt hours. And so if you look here at your bill, so this person, so again, let's look at this piece over here, right? And so they have different charges for sort of depending on what sort of time of the day it is or whatever. And so, yeah, so this box I circled here is what they charge for electricity delivery, and over here they charge you sort of a separate place for electricity generation. And this is the one where it kind of depends on exactly what time of the day. But again, it's done by kilowatt hours used, and so here they're using a rate of, looks like 0.19307 to calculate that. So you get the 109 kilowatt hours, and then the rate that they charge you for that, and it's 19307. So that's the dollars, and so we're taking 109 kilowatt hours and multiplying that times 0.19307, and this is dollars per kilowatt hour. So the kilowatt hours will cancel, and in this example here, it ends up being $21.04 for this. What is this? This the on peak. So again, just trying to tie in a little bit of real life here. All right, thanks.